Hi, everyone. We are Kinetic Solutions, paving the way to a green future. My name is Hunter Chan, and I'm joined by Caitlin Lobo, Radhika Agarwal, and Sayant Rath. A quick look at our presentation. We're going to cover the current landscape, our solution, how the technology works, a SWOT analysis, our implementation plan, the supply chain and operations, our financials, and finally, scalability.
Here is an excerpt of the data that was shown on the World Bank's website. From this graph, we can see that even though the amount of carbon dioxide emissions have reduced over the years, the amount of emissions are still high enough for it to be alarming for us, which is why we decided that as a team, we need to come up with an initiative to come up with clean energy sources. For our target community, we chose the University of Texas at Dallas. So at the University of Texas at Dallas, as we can see here from this graph, the energy consumption has been quite high over the years. If anything, it has been growing. During 2020 itself, the amount of energy consumption was 112 million kilowatt hours. At UTD, the main source of energy supplier is ERCOT. However, as a university campus, the University of Texas at Dallas has been proactive in starting a couple of sustainable energy initiatives, which include the use of solar power panels on campus, the use of extensive LED lighting, as well as reflective roofing.
So what is our solution? Kinetic plates are one of the most exciting and innovative pieces of technology emerging for sustainable energy production. With major developments to the technology in 2009, this has the potential to provide extra electrical power for almost no additional work. Seamlessly integrated kinetic plate surfaces installed on high traffic walkways are just waiting for foot traffic to actuate the plates, generate electricity, and power nearby existing appliances.
Here's a preview of our SWOT analysis. In terms of strengths, our greatest strength comes into the fact that it is a clean source of energy. There is no possible environmental degradation that comes as a result of kinetic energy consumption. Another way that it is a strength for us to use this solution is its seamless implementation. It blends in seamlessly with the infrastructure that our university currently has. One of its main weaknesses is the fact that a lot of energy is lost in the process of creating it. However, that proportion is lower than the energy that is actually saved. And the proximity of the place where the energy is used kind of makes it a weakness. However, our biggest opportunity is in the fact that it has limitless potential. It can be expanded into different kinds of services as well as different locations. It can also be used as a source of data in the future, and it can be used to track trends of foot traffic as well as population around the area. One of its main threats is the fact that over the period of time, even though durability has been countered to a great extent, it is one of its threats still. And it is also, there are also other energy sources which serve as the competitor to it.
All right, so kind of going into the technology behind these tiles, the secret behind how they work is a concept called piezoelectricity. Piezoelectric materials release energy when they undergo any sort of deformation or change in state, which is what we are harnessing here. So when a user steps on the plate, as you can see, there is an iron plate below it that moves inside range of a magnet that is attached to a piezoelectric bimorph. The magnet then moves towards to our iron plate, which deforms the bimorph and releases energy that is then collected by a generator. When the user moves his feet off the plate, the counterweight moves it the other way, which deforms it the other way. And then this slowly equalizes the plate for the next step. So kind of going into the implementation of how this is going to look on campus. So we are targeting building entryways with a 36 square foot grid of 16 1.5 square feet tiles. And then we have selected the buildings based off of the most foot traffic heavy academic, common area buildings, and residential buildings as well, with various numbers of entryways. And then not only do we want to actually harness energy, we also want to make students excited and curious about what these are. to increase the foot traffic in these areas. So this might mean including statistic panels that show sustainability metrics derived from Microsoft's sustainability analytics tool, and then LED meters to maybe show daily goals or how much energy that one tile or one strip has produced in a day. We would also like to upscale current campus landmarks, such as the Chess Plaza and the Plinth, which undergo a lot of foot traffic in order to access another source of energy.
Supply chain, operations, and installation. We will be sourcing our technology from PaveGen, a company based in the United Kingdom. Their experience developing the technology since 2009 makes them an expert in the field. With implementations in over 100 different countries with servicing a variety of clients, PaveGen will ensure a quick and reliable installation of the Kinetic tiles. Simultaneous construction for the 15 buildings across campus will take roughly 3 months.
So going into sort of our foot traffic, we assumed, as Sayan talked previously, that we had 3 common grounds: the academic buildings, the common rooms, and the residential units. Assuming a population of about 32,000 at UT Dallas, we assumed about 30% of our population would enter and exit the buildings at least twice with the academic buildings. Our common rooms would have an entry and exit of at least once with about 10% of our population. And finally, the residential units that are typical to our freshmen would have an entry and exit of about 1 time, including their dining hall. So following that, we sort of went into the energy produced per tile. We calculated the total number of steps to be about 209,000, and we included the daily steps per tile to be about 436 steps if we assumed that we were going to take 480 tiles. This gave us a daily energy produced per tile to be about 0.66 kilowatts per hour. The consumption of a unit of a singular bulb was about 0.1 kilowatts per hour, and this would be assumed that the bulb would run for about 24 hours, giving us about 2.4 kilowatts per hour. Thus, we calculated the daily light bulbs would be powered by a singular tile would be about 0.27. So on average, in an academic year, discounting holidays and weekends and vacations, we had that each tile would generate about 49 bulbs worth of energy. Finally, we got our annual light bulbs to be about 28,000. The annual light bulb cost would be about $96 in order to power a singular light bulb for an entire year. The cost incurred per light bulb powered would be about 2.8, assuming the installation cost of a singular tile to be about $140. And finally, we would have a savings of each bulb to be about $93. So what does this translate into? Our cost savings initially would be about 2.2 million for the first year, and then assuming we would install again another 100 tiles in the 4th year, we would reach about 2.5 million. Following that would be 2.7 million. So how much is this in terms of savings? Over the course of the 5 years, initially starting at about 2.2 million, we could actually fund about 36 full ride scholarships. So not only is this a sustainable venture, but it is also a cost saving and in addition to UTD's already existing environmentally free campus.
Coming to the scalability of our idea, the idea has limitless potential. It can be expanded to more types of surfaces, such as speed humps, other surfaces that experience a lot of foot traffic. It can also be expanded to other areas. So to start off, we could think of it in terms of other college campuses, like the UT Austin campus. It is also a feasible idea to be used in any place that experiences a lot of foot traffic. So some places like that could be the Las Vegas Strip, the Times New Square in New York, as well as the AT&T Discovery District in Dallas.
So to kind of talk about the actual technologies that we can implement in the future, just a quick sneak peek into the Libra speed absorber. It uses the same technology as regenerative braking to harness energy and can produce up to about 6 gigawatt hours per year, which is about that of a standard windmill. However, it is much cheaper, ranging from about $1,500 to $2,000 with no maintenance costs.
With that, we'd like to end off with a quote. Design shouldn't have to take a backseat to sustainability and making things responsibly. Thank you, and we hope you've enjoyed our Kinetic solutions.